Before we calculate the pressure on the piston face, I'll have to go through some mathematical details. This is a little painful, I know. Just see what we can get out of this. Often you'll see a function of a variable where the variable is complex, maybe even related to further variables. If you use the tick mark like that, it's basically a total derivative that you have to take the derivative of the function with respect to whatever lays inside it. That'll come up in a minute. We also need to know partial derivatives, where you're taking a partial derivative with respect to one of the variables occurring in the interior of that function, and that's a chain rule idea where you first take the this total derivative with respect to the total variable, and then you do the partial derivative of the argument with respect to the specific variable you're interested in. That in this case, the quantity up front here is recognizable as what we mean by f prime, and the quantity here is recognizable as just unity, because the derivative of x minus ct by dx is just going to be 1. So you come out with this answer. On the other hand, if you want the partial derivative on time, then you'll get this same total derivative here, which we identify as f prime, but then the partial on the time portion of this argument comes out to be a minus c, and so we get just a slight correction now. Now let's get the solution to our pressure on the piston face. I'm going to propose that the wave equation has pressure form of solution shown here, that there's a right traveling wave and a left traveling wave possibly emitted by that piston. These F and G symbols mean arbitrary functions at this point of those time and space variables. But we're only going to consider the disturbance propagating away from the piston face to the right, and that's called the radiation condition. I'm not interested in what goes on at the left, nor incoming waves from infinity. And so, that means we're not interested in reflections from the far end of that little tube. So our pressure field is going to look like this by assumption. Now we can put that assumed form into the momentum balance, and we'll talk about this in more detail later, but here's an equation that shows basically how the gradient of the pressure field will cause a change in momentum. So you get the density and then something like acceleration here, you see. So we put this in, and we end up then with a derivative on x is the same as the prime, or the total derivative here, with respect to the entire argument. The left side here is unchanged. Now let's evaluate this expression at the face of the piston. This is at the point x equals 0. And we now say that the velocity here is the velocity of the moving piston. It could be a function of time. The argument has reduced to minus ct. If I want to replace that derivative with a partial, I have to remember the chain rule that we had worked with before, and that coughs out this constant in the front, giving us a partial on time here. I view this as a little bit of a trick, so if some of you are puzzled by this, I can see why. Now here you've got a situation where there are two terms involved with derivative on time only. Now we can integrate with respect to time. In general, that would bring in an arbitrary function of space then as a constant of integration, but we're not interested in steady pressure fields in space, and so we won't worry about that. This actually is enough to give you the form of the function f of minus ct in terms of the density of the fluid, the velocity, and the speed of sound. And this is, in effect, our pressure expression that we'll complete in the next figure. I think this little proof is going to feel to a lot of people like lifting yourself by your bootstraps. It's sort of as if you assume the answer and then you show you know what the answer is. But it's self-consistent anyway, and it took some malice of forethought to set it up this way. Now the pressure on the face of the piston really is equated to the pressure in the fluid, which we had as our F function here was a pressure wave traveling to the right. And so if we set x equals 0 in that, it just gives this function evaluated at minus ct. And that is the pressure on the surface of the piston. So we're matching the fluid wave pressure to the mechanical pressure on the piston itself. And that actually then shows us, since we've already found the form of this F on the previous slide, that the pressure on the face of the piston at x equals 0, and it's the same as in the fluid for that matter, and for any time is rho v0 c. And so actually, this is an unsteady solution that is valid for any instant of time. This piston can be jumping around and oscillating. It doesn't have to be a harmonic oscillation. It can be any random motion, and in one dimension, you directly get the pressure to be rho vc. So it's interesting that the acoustic pressure is directly proportional to the piston speed. Now that's not obvious, because I work a lot in aeronautics where you have pressure forces like the form drag on bluff bodies, and the pressures go like speed squared. It's very common in turbulent flows and things like that. Often it's the square of the speed that's relevant. But this is linear acoustics, and we kind of luck out that pressure is proportional to the local velocity, and particularly on the face of the piston. The speed of sound enters, and here we have the density entering. So the medium itself has some effect, and as you might imagine, the heavier the fluid or the more massive per unit volume, the more pressure you get. The speed of sound's a little more mysterious, why you would get higher pressures for higher speeds of sound, but that's the way it works out. And I regard this then as kind of a fundamental checking calculation that you can use in other real-world situations. We do something like this in structural mechanics if we can refer everything to what a beam would do. And I have one friend who claims he can turn almost any structure into a beam if he tries hard enough. Well, in the like ways, you might be able to turn a lot of acoustic problems, surface pressures, into what would happen on the face of a piston in one dimension, and then realize that that's only a very rough approximation. A good part of my doctoral program at Caltech some 35 years ago had to do with doing flutter calculations at supersonic speeds. And at that time I was impressed with the linear piston theory. I knew that it had acoustic origins, and we understood how the flow going over a wavy wall acted in a similar manner to a piston moving up and down in a small tube. So I was impressed by that, and I thought maybe there are other fluid mechanics people who would like to be reminded about how linear piston theory works supersonically. Even though it's not an acoustic problem per se, it's an analogy, but it's kind of one that you can get for free with only a couple slides here. So we're now talking not about quiescent air, but rather air that's moving reference to a solid body. And if the body has shallow undulations, and there's a dominant mean flow here, capital V, then when the wall moves away from the dominant fluid field, you get the flow turning downward, and much as if a piston is being pulled away from the flow. In other words, the sense of the fluid flow is, hey, there's a piston there moving downward. Or if you reach an inclined slope in this direction, you get, hey, the fluid feels it's being pushed upward by a piston. In addition, there can be the unsteady motion of the wall itself, which would add indirectly. So this slope-like condition, and you can figure this out in a few minutes if you look at it, involves a vertical contribution of the flow velocity turned through the tangent of the angle, which is the slope here, dw dx, where w is the position of that solid boundary dividing fluid from solid. And then the unsteady part here would be how the wall itself will have moved in time as a particle of fluid goes from this point on to this one. The wall has moved upwards, and so really the particle sees this final direction of flow, which involves both the steady and the unsteady components. So the total vertical velocity, small v, is that shown here of a steady part due to the wall slope, and then an unsteady part here due to the wall's velocity. I believe Wally Hayes at Princeton University was the first person to point out the usefulness of this acoustic analogy for flutter problems. And we used that method widely at Caltech when I was a graduate student there for quite a range of panel flutter problems, curved panels, flat panels, and so on that were exposed to supersonic flow. The pressure on the wall surface using this piston analogy is rho CV. We interpret the V as the vertical component of velocity. That involves this slope term and then this unsteady term. Multiplying that out, some people think of this as an aerodynamic damping. This is a quasi-static force dependent on the instantaneous shape of the body. Other people would like to turn this into a Mach number relation rather than strict velocities, and they divide out in getting this form here. People call this linear piston theory, and it's used widely in not only in research but in some of the commercial codes. I know that in the MSc Nastran code it's used in as one of the alternatives for flutter calculation for supersonic wings. One thing that I often like to do is to compare different theories, if you can do that, put them on the same basis and see what they say about a similar simple physical situation. So I'm aware that there's a hydrodynamic field, there's an acoustic field, there's a linear piston theory, aerodynamics, there's a subsonic wing theory, thin wing theory, and so I was wondering, how do these different technologies compare? So I wondered if you took a small disk such as this one, and of course acoustics would be air at rest or another medium at rest, but then if this body from the side looked like a slender wing, this disk, but was suspended, let's say, on a spring in a damper, and might have some mass, it might have some so-called added mass due to the fluid going by or being around it, then it's a kind of a case that you could compare acoustics, hydrodynamics, linear piston theory, and subsonic wing theory. So I'm going to do that in the next couple figures. Now the question is whether the medium surrounding that disk will provide added mass, added damping, and added stiffness. And that is, these are fluid contributed causes to this motion of this small disk. You can write the differential equation of motion as shown here, and the lowercase m, c, and k matrices are the mechanical, physical stiffnesses that you or I would immediately see from the springs and so on. But the uppercase matrices m, c, and k are those contributions from the fluid. So an immediate question is, do you get these at all in a given fluid theory? But secondly, do they depend on frequency or velocity? And I'm trying to set up a small table here to illustrate this. Now, hydrodynamics, which you might call the father of all the fluid theories, assumes that the speed of sound is infinite, and this c now is not the damping coefficient that I've used up above. It's not a matrix, it's just a scalar. You also assume that there's no fluid flow, that the fluid is stationary in our particular problem here. I'm interested in just the quiescent hydrodynamics here. And it turns out you do indeed get an added mass. That's been calculated by many people. You can look in Lamb's books and so on, and often it's done by looking at the kinetic energy of the entire fluid field out to infinity and then finding some kind of an effective mass of the fluid itself. But there is no damping matrix nor stiffness involved in hydrodynamic theory. And that means even when the body is doing these small oscillations. Now this is a currently just a little flat disk. Now in acoustics, you assume again that we have quiescent fluid, that it's at zero velocity, and you do get a mass that depends on frequency in this case. There's no need yet anyway to assume that speed of sound is infinite, so your frequency plays a role. There's a kind of damping called radiation damping, which means that for an unbounded region and with no reflection then of the outgoing waves, your energy can be carried away. So it's a special kind of damping, and you can get a stiffness associated to the medium, and it depends on frequency. So this is a rather rich problem, it turns out. Subsonic wing theory, call it thin wing theory, would be much less than Mach 1, say up to a couple hundred miles an hour. The one thing about slender wing theory, or subsonic thin wing theory, is that you can get vortices, and these are what ultimately give you the lift. Now, you do get an effective mass, you do get damping, and you do get stiffness-like quantities when you do an oscillating wing type theory. Linear piston theory, you get Mach 2 to 5 range typically. Sometimes people will apply it a little bit lower, maybe down to 1.5. Turns out there is no mass effect, but there is quite a substantial damping. That's due to that unsteady term, the dWdt term, if the wall's moving. And you also get a stiffness-like term, which is quite dominant, and a non-conservative type of stiffness that causes flutter. I think there's some viewers by now that are wondering, what the heck is this guy doing? He's wandering off into other fields, and I wanted to find out when I talk whether my guy next to me can hear me or not. It's just my general curiosity, and I'm enough of a newcomer to the field of acoustics that I'm curious and interested in how this field fits into other areas that I've seen. Let me press that discussion for 3 more figures, just in a laundry list of comparisons here, and really I've already spoken to some of these in the previous figure. Starting out, acoustics versus hydrodynamics. What they have in common is that they're small disturbance theories, and there's no vorticity or lifting type theory, at least for that stationary disk there. The disk that in a quiescent field of fluid. There's no damping in the fluid in this case for either case. In other words, the fluid, the medium itself, doesn't internally have viscosity. Now, we did get that radiation damping out of the acoustics, but it's an unusual thing. And that's one of the special things to acoustics, is you get the radiation damping out to the far reaches of space. You can have compressibility in the acoustics problem, which would lead to a finite wave speed. You do get that the wave speed is constant, not a function of the frequency. The thing that's special to hydrodynamics is that you get an incompressible medium assumption, and then you have infinite wave speeds. So things happen instantly, and that's why it's been a nice area in which to calculate added masses, because things happen instantly throughout the whole space. Next, we talk about acoustics versus subsonic wing theory. Common assumptions are both small disturbances, and in both cases you can lose energy through damping mechanisms. The thing about acoustics is that you can include the compressibility of the fluid. The finite wave speed is always true. But we don't get circulation in the acoustics theory for these infinitesimal motions in a quiescent fluid, and there's no damping per se in the fluid itself. The wing theory is generally taken to be incompressible, and it can have circulations. Once you get that mean flow past that little disk, then it can shed a vortex, typically called a horseshoe vortex if it's a slender, if it's a wing that has quite a span. In a disk, I don't know quite what that vortex shedding would look like. It might be kind of interesting anyway, but there would be this circulatory effect of the flow swirling like that. Lastly, we have the comparison of acoustics and linear piston theory, which is a supersonic theory. Common assumptions given here: small disturbances, compressible fluid, finite wave speeds, no circulation in either case, so you don't get lift by circulation in the supersonic case. It's by just pressure differences among the surfaces. In acoustics, where there's no damping in the fluid itself, even though you can have the radiation energy loss. In piston theory, you have very localized effects, and there's no time delay. One thing about piston theory is the way that flow sweeps past a wavy wall is that it only feels locally the pressure of that piston. So you've got a bunch of one-dimensional problems going in a vertical sense as we drew the wavy wall. And there's no time delays. You don't get buildup of vortices and so on that can affect what's going on upstream as you can in subsonic theories. So it's kind of interesting to look at these different cases, and don't let them confuse you. These aren't really important for acoustics, except that you may also have seen some of these other fluid mechanics areas and wondered if there was any relation with acoustics. Now, from this point on, we're going to go into more of the theory of numerical acoustics, and we'll start out with a lot of classical ideas in the second lecture and then go on into the different boundary elements and finite element versions.